Hey everybody, this is Larry. This is day 23 of the November Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this problem. Okay, so today's problem is 952, largest component size by common factor. Is it hard, supposedly? I am solving this live, so if it's a little bit slow, let me know. I feel like I've solved... Ooh, yikes. Ram into something. I feel like I solved something close recently, but maybe the common factor ones are always kind of have the same idea-ish, at least without being too much. But let's read this, because no, maybe I'm just confusing problems. Okay, let's see. So the end nodes, they're under and if they share common factor other than one. Okay, return the size of the largest connected component in the graph. I feel like there are a couple of similar problems to this, maybe harder ones now, but the basic idea is that okay, there are all these things. There's all these. Let's see, right? There are n numbers. Let's say the n numbers, and basically anytime there are two numbers, we can put them in the same component if they contain a common factor. And I think the first thing I would say is that when someone say component, especially things that are transitive, or where the transitive property holds, the first thing I would think about is union find. And yeah, and that's going to be a key in this problem. And then the second thing is that, okay, look at n, and n is 2 times 10 to the 4th. So n squared isn't going to cut it. You can't just do a naive, for every I, for every J, union find the things, right? So that's kind of out of the way. And the way that you would do it, of course, is just by using GCD or something like that, right? And then the thing is that you think about all these components, and instead of kind of instead of thinking about each component with respect to figure out about each component, instead of looking at each node as a thing, you think about the equivalence classes, right? Of okay, that you can think about it backwards maybe, right? With respect to kind of almost like a sieve like way of approaching it. And I'm saying sieve as in the sieve of Aristotle's. I'm always saying it that wrong, so apologies for that. But yeah, and then the idea is that okay, what does that mean, right? That means that all the numbers that have a 2 in this factor, right? Then it is all the numbers that have a 2 in this factor, all the numbers have 2, they all will be in the same component, right? So that, and what does that mean? That means that now, instead of doing this for I for j thing, you can just be like, okay, all these, group all the things that have 2 and group all the things that have 3 in the factor, and so forth, ... And then another component of that is try to do that in a fast enough way, which we'll have to explore. I am solving these live, so if it's a little bit slow, fast forward, because this may actually be a little bit messy. It's been a while in terms of complexity, because I don't know if it'll be fast enough, but conceptually that should be okay. So then, for example, what that means is that, let's say you're given a number 10, right? What does a 10 mean? Well, a 10 is 2 times 5, of course. And that means that it connects all the numbers that have a 2 in its factor and a number that has a 5 in its factor, right? Because now you can think about, like now the 10 allows all the numbers that have a 2 as a factor to connect through all the numbers that have 5 in its factor through 10, right? And this is, of course, this component thing, or this transitive property. So then now 2 and the 5s are all connected by that number. And then now, with all that said, we just have to return the size of the largest connected component at the very end. Yeah, okay. Let's think about how to get to this. Um, yeah. Let's see. All the numbers are unique. Okay, so I don't know that all the numbers are unique really matter, but it is a thing. So yeah. Um. Hmm. Well, in that case, we do want to use the sieve in some way because um basically we want to get the is it enough to do we have to explicitly factor everything? Or can we just like represent each number by its lowest thing, right? Because okay, we have a 3 and 6. No, you have to do it because you have like 3 and a 6, then you have 2 and okay, fine, right? But yeah, but given that each number, so what I'm trying to do is right. What I just said is that we break each number um, into the factorized form, and then those numbers are connected, right? So with for example, we have 10, then the equivalent classes of 2 and the ones with 5 in the factors, you connect them, right? But of course, if you do it naively, if you do something like for x in for x is nums, and then you do maybe something like for or like while I times I is and dot dot dot, right? Like you try to factorize x. The problem is that if 10 is this would take the square root of 5 or square root of 10 to the fifth, which is let's say like 10 to 6. Maybe that's fast enough actually. It's getting a little bit close, but maybe that is fast enough. But because that's roughly 10 to the third, 2 times 10 to the 7-ish. Is that fast enough? What's 2 times? That's like 20 million. Maybe that's fast enough, but it's 20 million, not cheap loops, right? Because we have to do union find on each of those things. So maybe that's why it's a little bit yucky. So the thing that I would think about next then is to optimize this, right? Because we know that so we want to go through it as quickly as possible. So then we do the sieve on 10 to the fifth because that's the max number. And of course, using the sieve, we still have to be careful, of course. But I'm just googling how to spell this because I'm always embarrassing myself on how to spell this. Okay. Yeah. So we use the sieve, and the idea, and well, one thing about the sieve, and maybe this is more trivia, in that I don't really know a great way of explaining how. I mean, you could sum the series, but basically, this one's in n log n time, where n is the biggest number. Not to be confused if this n, or so yeah, so we can get to it, and yeah, and because of that, then now you know that this one's in roughly speaking, 10 to the fifth times. What is that? Times 10 or something? No, not no, more than that. 10 to the 6. What's log base 2 10 to the 6? Eight, no, like, well, 20 is whatever, right? So like whatever, 16, 17, I don't know, right? So that's gonna be fast enough because that's just like million, right? And then after that will be fast enough. So that's why I'm able to kind of think about this. And then now we just have to think about how to do the sieve, right? So now this is to be honest, I haven't done this in a while, so I'm a little bit just sloppy. I mean, I know how to do the sieve, but I don't know how to do the version with the like. I know how to do the prime one, but I have to think about how to do, or not how to do it, how to write it, because Python's always weird with the for loops. But yeah, but maybe this is fine actually. So you start from 2 to m, let's just say, where m is max number, and of course let's just do oops. Okay, so yeah, so then now we go through, we know that, you know, if let's just say factors then is equal to is this fast enough? It's probably okay. Let's just do this. Right. So let's say we have this. We have factors of. I think 1 is the weird one, maybe. Huh. Actually, I didn't even think about the 1 situation, but because. Well, it has to share a common factor greater than 1. So the 1 doesn't. Basically, we could just throw away the 1, I guess, because 1 doesn't do anything. Because once, yeah, okay. So then we don't have to do anything here. Okay, so then now if length of factors sub I, if this is equal to 0, that means that there's no smaller factor of I than this is prime. So I is prime, and then we just yeah, so well, I guess here we can reuse it, but just to kind of make it easier. So yeah, while j is wait, I guess I do this because for prime, all the other ones are kind of taken care of. Do I need this? Let me think about this for a second. So yeah, if you do the prime sieve, then this is okay. But I actually don't know if this is okay for the other one. But yeah, okay, let's do it this way then. So yeah, so factors sub j, we append I, right? So that's basically it, really. Oh well, that's basically it, except for we have to add I, and that's basically it for all the factors. Just to kind of make sure, convince myself that this is fast enough, I am gonna, oops. I am gonna just run this just to see what the performance is. Okay, so it takes 88 milliseconds for 100,000, so that should be okay. Yeah, and if you want, you can actually just like do enough test cases just to see. And then now we have to do the union find one, right? Because now we have all the factors. Maybe this is going to be a little bit slow. I don't know. We can rewrite this in a different way, but I wrote it in a very naive way. So we'll see. Yeah, I wrote it in a naive way, and then maybe we can do some like relatively small optimizations. Let's print it out real quick. What goes up to 35 on a sieve? So 0, 1, 2. I think I have to do something like factors sub I is equal to. We have to append I, because we have to do 2, 3, 4. Okay, yeah, it's because it should have itself. I think there's another way to represent this, by the way. So yeah, so this looks good conceptually. There is another way of representing this, which yeah, which maybe I'll get to in this. Maybe I'll get to later. But the idea is that, okay, you have a 2, so then actually you just go back to the parent, which in this case is a 2. So then, yeah. Because here you can just store one of these and then it'll get you to the other one, right? Because for 6, if you store 2, then 6 divided by 2 is equal to 3, and or the other way around. So I think that's probably okay. Yeah, maybe that's fine. Is that faster? I don't know. It is less memory, if nothing else. Anyway, we can think about it later if we run into timing issues. Okay. So then, yeah. So then now we just have to do the union find, and I know maybe this is not as popular as whatever. But I actually, okay, yeah. But I actually don't. I usually implement it every time because it's like 2 for loops. But I also do a variation of it. I don't do the sort. Oh, is it not sort? But like merge by rank. I just kind of just do it. So okay. So yeah. So let's just do parents is equal to. Let's just a hash table thing, and then now let's just do union find of 2 numbers, which is just one number x. So if x not in parents, then parents sub x is equal to x. Just base case, and then if parents of x is not equal to x, parents of x is equal to you find parents of x, and then at the very end just return parents of x, right? So that's like, you know, basic union find stuff. And then the union, I have 2 components. It's just find the parent of a component, find the parent of b component, and then parents of ua is equal to parent is equal to ub, right? And that's pretty much it, really. I mean, that's union fine. Hopefully I say that and I don't make a mistake. But then now we can do for x in nums. Oh, we do have to. I made a mistake here, to be honest. Actually, usually you don't need the component size, but actually for this one, obviously you have to get the component size because that is the tree to bomb. So let's actually add that here. Yeah. Okay. And you only have to care about it in the right. And then here, so this will save us a little in the future. Yeah, just because we need to know the size later. So okay, so now we connect them. Let's see. So what we want to do is for all the factors of this number, we want to, you know, let's say that because it is transitive, right? So one thing that you maybe do naively is that, you know, for example, if a number has 10 factors, though that's not really that possible given, is it 10 factors? I forget what the max, I mean, I could derive it, but it's fine. 10 to the 5th, it doesn't have that many factors, but the point is that let's say a number has 10 factors. If you do it naively, you may do something like 10 times 9 over 2, you know, and choose 10 choose 2 pairings of and choose 2 pairings of unions, right? But of course, because this is transitive, you can just do O of n number of unions. Like in this case, you just do 10 unions or 9 unions, I guess, because it is transitive. You just have to use one number to do it, or adjacent numbers. It doesn't really matter. Everything is transitive. So as long as you connect one to the component at the time, that's fine. So yeah, so the way that I would do it is maybe for y in, what's it called, factors sub x, right? So we union y with the factors sub x of 0, right? And that should be good. Let's start with the first one. Yeah. Okay, so that should be good. Of course, and then now we just have to get the component size. How do we want to do it? Because now there are x components, and then you just get the size, right? Get the maximum size. So you can do a couple of ways, but for example, you can do something like you find of x, and then sizes of this, right? I mean, this you can actually do better than this, but I'm just doing for illustration, though it might lead to time limited exceeded as a result. Okay, nice, wrong answer. How did I? But that's conceptually the idea. But it is not right though, as you can see, for some reason. Dong dong dong. Did I miss it? Parents of A is equal to parents of B, so B swallowed it. Yikes. Right. Okay. Let's see. Maybe I get something here wrong. Let's debug this real quick. I think that ideas usually should be okay. Maybe I made something up. So 3 and 2, okay. Did I mess something up? What's the 4? 4 should have a 2 and 2. I guess it doesn't really make sense. But let's look at my sieve anyway, just in case. Oh, because 4 is... Okay, no, that makes sense, actually. Okay, so we combine the 3 and the 2, 5 and the 3, and 7 and the 5. So we definitely should have more than just one component. I might have messed up the size, though, because I kind of just hacked it in. This thing, is the path compression being weird? Let's see, UA, no, it should be the parent, so we should be okay. But we are clearly not, so let's see. This looks funky. Okay, so parent is right. The sizes are wrong. Have I not done the size? I guess I haven't done the size. But all the parents are correct, right? So we are good here. You can also do it in another way, just by doing a for loop and then counting the number of same parents. Though this should be right. What am I doing wrong? Dun, dun, dun. Why is this wrong? Also, this one has a 3, so why am I... Something is just a little bit off, clearly. Just the sizes are just not maintained correctly. Did I do this right? Maybe the path compression? Let's see. Okay, so AB 1 right? Yeah. And then sizes of UB. How did we lose some information here? Oh, no, the size is right. I am blind. I think I just glanced over it. Oops. So sizes is right, but maybe I just did this part wrong? For x's and nums, sizes of u find of x should be right. Why is that returning me 1? Yikes. Debugging. Why am I always debugging? I've been like really not great. Okay, so oh, I am being dumb. That's why. Okay. So I was wrong on this because I am doing it over x, and x doesn't really have components because we said we're trying to figure out the biggest component based on the factors. So I made a mistake here. Okay, so that's not right. So what we want to do then is we can do it here on a... I think that's where I should have done it anyway. I just was opting for something that I thought may be a little bit better, but maybe not. So yeah, after a union, we can look at sizes of you find of the first factor, right? Also, because I looked at it a little bit wrong as well. So, okay, so this is still wrong. But I looked at the wrong size for this one. Why is this wrong? This also, like, this setup is a little bit hard to debug or look to debug. Let's see, 1, 2 is 4. So okay, so so I mean, at least it's printing the right thing, but why is that? Let's see. What are we unioning here? Oh, I think I'm messing up the size. And what I mean by that is, I think I'm handling the size in a weird way. Because basically we have these components. Okay, I am just handling this in a really weird way. Okay, let's not do these sizes. I think so. This is the sizes of these individual things, but I'm handling size in a really weird way. So I don't think that's right. Because it is the size of the number of the number of factors. Like it's a combination of factors on the thing. So this is just not right. Wow, man, I did this wrong a few times on here. Okay, so actually we had it kind of right the first time, but we just needed to do this. We look at the size of the component, and that's not true here. What we do is that, okay, so this is the parent, and then we just kind of, let's just have a collection.counter. And then count of this, and then now we just do max of count values, I think. And that should be okay. I said that before though, so we'll see. Okay, so that looks good. I just confused myself because I talk too much sometimes. When I do it on contest, maybe I'm more focused. I don't know. But yeah, but basically what we want to do is that, okay, for every factor, for every number, we represent it by the unique factor. The first factor, it doesn't matter as long as it's, because any of those factors are possible in one of the components, right? So like they're all looking at the same component, meaning that if you look at any of these factors, you find will return the same parent anyway, because if it's just by definition because of all these unions. And then now you increment the count by 1 because you could actually have done it here as well, right after the combination. No, you can't, because it may combine later on. So yeah, so now and then you just get the max of all the counts of that, the largest component, because this is just saying, okay, I'm in component 2 or something, right? Okay, let's see if this is fast enough. That's my only worry. Oh, apparently I already done this twice. Ooh, no. Oh, I forgot about 1. Man, I'm very sloppy today. I don't know why. Let's see. I've done it twice and it makes me sad. But yeah, what do we care about 1? I think we just ignore 1, but I forgot to handle this because 1 doesn't have any factors. So yeah, probably handle this in a better way. But right now I'm not really thinking, and I think that's the only edge case. Because I even talked about it earlier, but I was got confused by all the sizing stuff. Okay, let's give it a submit again, and hopefully we don't time limit exceed it. That's the only thing I worry about. Though I should have worried about the one time exceeded anyway. But okay, 602, right? I forgot about celebrating 600 days. Core did it as well in my Discord, so come join in Discord. But yeah, but that's all I have for this one in terms of implementation, thankfully. Even though this was much slower than I think I did, probably even last time if you ask me. But yeah, definitely check out that video, see what happened that time. I don't know how I'm so today. But yeah, so this is the sieve. This is, let's just call this m log m, where m is the largest number. The union find, I just say, roughly O of 1 per operation. I know there's stuff about inverse Ackermann function. Just pretend this is O of 1. It's fine. And yeah. And because all this stuff, you may ask, well, what's the longest complexity, right? Well, this is actually unique. So this part of the complexity is a little bit harder to analyze, but because every number is unique, that means that for every factor that we generate, we only do one union operation, and we only generate m log m factors just by definition as well, because every loop here is going to be total m log m, right, of all the components all together. So therefore, all this is m log m, even though it's kind of tricky to see, or at least that's the upper bound. It's not the tighter bound because there's n in there as well, but roughly speaking, I think that's right. Excuse me. And then here it's just O of n, right? So that means that this is going to be dominated by this, which is O of m log m time. And for space, this is factors, which is also O of m log m space is the way that we did it, because we put all the factors together. You can actually, there is an optimization that you can do, as we said earlier, which is that instead of appending every to get all the factors, you can just actually put one factor, and then you can divide to get that, to get another factor, and so forth. And if you do it that way, it's just O of m space, right? Because you have O of m numbers in the factors. So, okay, let's go over the complexity. So time is O of, let's just say O of, maybe O of n log n as well. But that gets dominated by m, so I'm just going to write it this way. For space, O of m log m here, but you can optimize it to O of m. Yeah, that's pretty much what I have for this one, even though it took a long time. Yeah, what did I do? I'm just curious how I did in the past. How did I make, I was saying remember the one, but I forgot. Okay, so I actually did it roughly the same way, except for actually here, I did it the way that I said with respect to, I thought this would be too slow, to be honest, but I did it, I didn't do it with the sieve. I did it with the square root way. Okay, I mean, yeah, okay, I did it with the square root way, and it is fast enough, though it's a little bit slower apparently, but it's from a year ago, so who knows. But I got the other parts are right. So apparently you could do it with the square root way, and it probably would have been much faster. So I don't know. Sorry, it'll be. I mean, clearly it's slower, but I mean, it probably would have been faster to write, because I think I had to do some proving here. But at least it means that we learned something new. I had to, reacquaintance myself with this sieve, so it's fine for me. Anyway, yeah, that's all I have for this one. It's Monday for me, Tuesday for you maybe. Hopefully it's a long weekend. Happy Thanksgiving, or come back tomorrow. I don't know. Do whatever you need to do. Anyway, stay good, stay healthy, to good mental health. I'll see you later, and take care. Bye-bye.